All right, let's look at a couple of methods of approximating definite integrals. First one is called the left sum, and the second one is called the right sum. All right, so let's look at the left sum first. All right, so we want to find the approximate the value of the definite integral from a to b f of x dx. Right, and if I draw a picture of f, let's say it looks like this. So the value of the integral represents the area under the curve, right? So which is shaded in blue here. All right, so we want to approximate the area, right? And we have three straight sides, which is nice, but you can see that the top is a curved side, so that makes things very difficult. If you have a square or rectangle, we can just do a base times height. But since it has a curved side, we don't really have a formula for it. All right, so what we want to do is I'm going to do this. I'm going to slice into skinny pieces and then try to approximate each one using a rectangle. All right, so let's do that. All right, so first we have to chop things into n equal pieces. All right, so going from A to B, I'm gonna chop into n equal pieces. So I'm gonna kind of slice it vertically like this. All right, slice the region like this. All right, and I'm gonna keep on doing it. And I'm gonna say so keep on doing that. And let's say this is the last piece like that. All right, so since they're n equal pieces, we are dividing the length from A to B, which is B minus A, divided by n. So we know that each one, so we're going to call the width of each one is called delta x. So I'm going to write, let's see, so this one right here, each of them is called the delta x. Right, which can be found easily since the length of the entire interval is b minus a. We chop that into n equal pieces. So b minus a over n is the value of delta x. Right, so for each piece, this is what we're going to do for left sum. Right, so let's look at the first piece. Right, so you have left endpoint and the right endpoint. So what we're going to do is go straight up on the left endpoint and look at the value of the function, and we're going to actually chop this guy off at that height. So you would have a rectangle with the height determined by the left endpoint. So that's where the left sum comes from, right? So the area of this rectangle is fairly easy to find. All you have to do is base times height, right? So the first one, base is delta x, so we already know that, right? And this is just going to be simply plug in the first value. Oh, actually, I forgot to name these values. All right, so first one value, I'm going to start with x0, right, which is same as a. And the next one, I'm going to call it x1, next one x2, and so on. And since they're n equal pieces, so this the one before the last is xn minus 1, and a b is exactly the same as x of n. All right, so base times height. So we can height can be found by plugging in x0 into the function, because here the value is f of x0. So base is delta x, height is f of x of 0, s of 0. Right? So that's the area of the first rectangle. Right? Then we just keep on doing it. So you look at the second piece, we look at the left endpoint and determine the height using this f of x1 value. And then here is the rectangle right there. Right? So the area of that is going to be base is again same as before, delta x, but height is determined by f of x1. All right, And as you can see, you can just keep on doing that. So I'm going to just say I'm going to keep doing that until the last piece is going to be this rectangle right here. So this is the very last piece, right? So the base of that is, as always, delta x, right? Height of that is you plug in x n minus 1, so you have f of x n minus 1, right? So to make it look better, we can pull out the delta x, because delta x is a common factor. So I'm going to pull it out at the end. So we're going to put delta x right here. And then you have first one is f of x0. Next one is f of x1. And I keep doing that until the last one is f of xn minus 1. Right? Alright, this sum is called the left sum because we're using a left endpoint of each interval to determine the height of the approximating rectangle. Alright, so similarly, we can define right sum. Right, so delta x is as before exactly the same, so it's a b minus a over n. Right, so let's look at the right sum. All right, so we're gonna again chop that into n equal pieces. So we're gonna do that. So skinny pieces here. All right, just keep doing that until the last piece. All right, so the naming is the same. A is called x0. Next one is x1. Next one is x2. And the one before is xn minus 1. B is same as xn. Right? So this time, when you determine the height of each rectangle, we're going to use the right endpoint. Right? So the first one, right endpoint would be at the x1. So we plug in x1 into the function, and we have rectangle which is taller than before. Right? Then area of that is the base is delta x, height is f of x1, right? So you see the difference. Left hand point, you start with f of x0, but now for the right sum, you're going to start with f of x1. All right, so the next one, the height is determined at x2, so we're going to do f of x2 times delta x. All right, so the intermediate terms are exactly the same, but the ending term, all right, this time, if you look at the last rectangle, since you're using the right endpoint, we're going to use xn to determine the height. So this last one is f of xn delta x. All right. So as before, we can pull out delta x. So you're going to have f of x1 plus f of x2 plus the pattern continues until f of xn, and everything is multiplied by delta x. All right. This sum is called the right sum. Right, so you can see the difference. The difference is we're starting from f of x1, ending at the f of xn. But here, for the left sum, we're going to start from f of x0 instead of x1, go all the way to f of xn minus 1. It's shifted a little bit. Right, so those are called the left sum and the right sum. Right, that's it. I hope that this was clear.